All right, so it's a great pleasure to have with us Srinivas Narasimhan. He is a professor at the Robotics Institute, Carnegie Mellon, and also the incoming acting director of the Robotics Institute.
I don't know if this is being recorded, so
Okay.
nobody watches these things anyway.
Okay, so Srinivas has had an amazing trajectory in computer vision, computational imaging, computational photography, graphics, starting from his groundbreaking work back in the early 2000s. In fact, 2000 was his vision in bad weather work. That was for his PhD, which started basically a whole new area in vision. Got a best paper prize for that. That was the first out of many best papers, including one together in 2019. He had a MAR Prize honorable mention at ICCV 2013, and a long list of others, including some with old colleagues and alumni. So it's a great pleasure to have Srinivas here, and let's give him a welcome.
Thank you. Anybody can beat the number of awards that Kiros. Honestly, Kiros is a great inspiration, and I think in imaging, and I've had the greater pleasure of working with him and many of you, and reading your papers. And I think this morning your thesis was excellent. I loved it. The number of talks that we hear about computer vision. By the way, can people on Zoom somehow hear me or something? I don't know. I'm assuming it's okay. Otherwise, somebody will yell. Computer vision is something every day in the morning my student sends me. So this is the latest amazing thing that is happening, right? And if you read this title, Light, Heat, and Sound, you might be thinking, hey, this is a multimodal large vision language model that combines video from visible spectrum and thermal camera and audio. That would be great, but that's not what this talk is about. Okay, this talk is about something that is much more fundamental, much more basic level. So we are thinking about light, heat, and sound as waves, right? And we know a lot about it from physics, right? And so if you think about the work that is happening in computer vision, 90%, conservatively, 90% of the work is happening on light that is in the visible spectrum, right? That's what is going, maybe 99%, I don't know. It's not to say that no work is happening elsewhere, but a majority of that is happening. Why? Because our experiences are also visible, right? Makes sense, right? Absolutely makes sense. But computer vision has been historically chasing human vision, right? And that's one of the reasons we are trying to match the performance of human vision. But there's a lot more in the environment, like what we saw in Mian's thesis, right? Just a boring old room has so many things happening that you don't really pay attention to, right? And so in this talk, I'll show briefly maybe about 10 different projects that tries to look at the interplay between the different kinds of waves, light and heat and sound and so on. Cases where one modality gives rise to another one and so on. So these are things that is known in physics. So I'm not a physicist, I'm not deriving new physics here, but we are trying to exploit it in computer vision, right? And so please feel free to interrupt me and at any point. So let's look at heat first, light and heat. This is the afternoon, so maybe you're putting a coffee pot or something and heating it up, right? And so you have a kettle on like this. What are the things that are happening in heat? And this is something that you might have studied in high school or college. You have radiation, so any hot object radiates light in particular wavelengths, right? The sun is so hot, it is radiating light in the visible spectrum as well as the invisible spectrum. But if you think about all the objects here, we are also radiating light, right? depending on the temperature that we have, right? And it's not just this, but you have, movement of fluids. This is what we call convection, right? It could be steam, it could be air, it could be other fluids. And of course, the most important part is conduction, right? So if you think about it, if I'm heating up the water, the surface of this kettle itself is getting heated up, right? And what is the energy here because you have atoms and molecules that are just vibrating, and that vibrational energy is being transported as heat, right? So heat is really a mechanical wave, right? It's not an electromagnetic wave like light. It needs a medium to go through, and so you have, and this is what we call conduction, right? And so we have these kinds of effects happening everywhere. In fact, in this room with this light source, it is heating up objects subtly, and we can see all of these effects. Okay, and so now one interesting thing from a computer vision perspective is that this conduction is shape dependent. Why? Because it's sort of heat is being transported through the volume, through the surface, right? And so there must be a relationship between that and shape, and that's what we like to do in computer vision as well. So think about thermal camera, what it actually is measuring. And this is something very interesting, and we looked at a lot of thermal imaging literature, but it's not really handled very well. So let me go through it a little bit more carefully, right? And so a thermal camera is a camera that measures light, radiance that reaches. And in this case, a long wave IR camera measures light in 8 to 14 micron range of wavelengths, right? And so everybody understands this. This is a long wave IR camera. And so what you can think of is light coming in that wavelength that is being reflected by objects and then goes to the camera. That is just like light in the visible spectrum, right? Whatever we know about light, what it does in the visible spectrum, it also can do in these other spectra, right? So we think of this part as the light transport component, right? And this is something that we have been talking about. I think Kiros has done a lot of work. You guys have done a lot of work. Whenever you have reflection, refraction, transmission, all of these things are light transported this way. But of course, as I said, the object is hotter for some reason. Maybe you heated it up in some way. The light source could already heat the object, or maybe you just put it under a flame or something, right? And depending on the temperature of the object, you get emission, right? And this is emitted light rather than reflected light, right? And this camera is actually measuring a combination, in fact, a linear combination of the two types of light. Right? One is the light that just goes around like what we do in the physical world in the visible spectrum. One is the emitted light, right? So very loosely speaking, you have a thermal image, which is a combination of two things, reflected, transmitted. This is something that we all know. And then there is this emitted part, right? So if I want to understand these components, first I have to figure out how to separate these things, right? And so here's how we do it, right? Because the camera is measuring the sum of these things. So how do I separate this out? So imagine again our coffee pot or something, and you're going to heat it up, and I'm trying to pour coffee. So you'll see my reflection on this glass, right? So that part is light transport, right? Anything that you say, you stand in front and you do something, you see the reflection, right? Now, if you observe it with a thermal camera, right? And by the way, I don't know whether you can see this or not. This is the water getting heated up. I haven't played the video yet. But by the way, heat doesn't just immediately go as fast as light, right? So it's like watching paint dry. Very slowly it moves. But what's interesting is that you can see that there is my student here doing something. That is the light transport component in this. What we are trying to show here is there is a lot of heat transport, but a little bit of light transport that is happening. I'm not even sure this display is showing it. Maybe that display is showing it.
Yeah, you can see it.
Yeah, you can see it, right? You can see it. And so both are different forms, light, but their origin is different, right? And so you can write this equation that is just because light is linear, right? That's what you're measuring. You have a linear combination of the two terms. Now, whenever you have a single equation with two unknowns, you just cannot solve it, right, uniquely. And so what you do is you add another equation, right, somehow. Where is that other equation coming from? One way to do that is to use different spectral bands in the thermal spectrum, right? Just like RGB in the visible, if you have lots of filters in the thermal, and so if you use two of these things, you get sort of two of these equations where the emissivity is changing between the bands, but other things are not changing, right? And so it becomes very simple to actually separate out, what is light reflected or transmitted through this thing versus what is being emitted, right? And so we didn't have anything about the prior. We didn't know whether something is moving, whether something is moving in a particular way, or this is just analytically, it comes out of this equation, and you can do that, right? And if you want to just see how this heat is moving, it's not great to show this video because it's very slow. What we typically do is something called isobrightness contour, and you can sort of see the heat moving on the surface of the kettle itself, right? And so we have a very simple way to separate out light transport versus heat transport. So everybody understands the difference, right? One is about emission, one is about reflection or transmission, right? And so now you have something like this. What can you do with this, right? And so here is a teddy bear, and I'm showing a transparent teddy bear because, in computer vision, it is hard to reconstruct these kinds of things. And there are some works that are really good, but generally it is hard to reconstruct these things, right? But if you see it in the heat transport, no matter what the reflectance properties of that object are, there is some light that is being absorbed and some heat that is being formed, and that heat is transported across the surface, right? In fact, the heat is also transported to regions where the light doesn't go, right? So if I illuminate it from one side, you will not see the light on the other side, right? Typically, it's a shadowed region, but the heat actually can go there, right? So that's one of the benefits of using heat transport versus light transport, right? And so you can look at this conduction, and then you can use good old heat transport equation. This is the long heat transport equation. There are lots of terms here. I don't think you need to pay attention too much to this. But on the left side here is saying, what is the rate of change of temperature? This is your video. This is your thermal video, right? After we have removed all the light transport stuff, this is your thermal video, right? And so the first term here is called the absorbed heat flux. So whatever generated the heat, how much heat was generated before it was transmitted, that is called this absorbed heat flux. It's called the source term, right? And this term is called the radiation term. This is the convection term, and the last one is the conduction term. Right? And so if you use a video and you try to fit this equation to that video that we saw, you can estimate these components, and especially you can look at this conduction component, and this is shape dependent. In fact, this is a Laplace operator applied to the mesh of the surface, right? And so think about this. In computer vision, there is a lot of methods that says shape from X, right? Shape from shading, shape from turbulence, shape from texture, defocus, lots of shape from X methods, right? In most of these things, you're either estimating the surface normal, right, the orientation of the patch, or the distance in stereo and so on. This is the first method that gives you a different kind of cue for shape. This is an intrinsic property of the shape. It's called the shape Laplacian. It has to do with the edge lengths on a mesh on the object. It is not about the surface normal at the object. It's about the edge length, right? So it's an intrinsic property. So if I move an object further, its depth changes. It's called an extrinsic property, right? Whereas surface normal, if you rotate with respect to this, surface normal changes. The intrinsic property means it doesn't change under these transformations, right? So this gives you a way to obtain the intrinsic shape properties, and after that you can actually lift it to surface normal. And so here's a couple of examples. You can obtain shape of this object, right? So you have a video, and you fit that heat transport equation, you get the Laplace term, and that shape Laplacian can be lifted to estimating shape, right? And so this is, of course, these thermal cameras are not of the same quality as a visible camera, right? Or a laser range scanner. So this, shapes are not perfect, but it's still pretty good. So for a few centimeter object, there is 1 millimeter error. And so that's pretty good, right? Now, the nice thing about using heat is that you can actually go beyond light. That means you don't need to have light to do this experiment, right? In fact, you can use a hot air blower to heat something up. It could be completely dark, right? So where is the heat coming from? That could be coming from many things, right? Not just light. And so you get this kind of a conduction term, and you get the shape associated with it, right? And so it doesn't have to be about heating. You can also look at cooling, right? Naturally, you can cool something, and you can also get the shape out of it, right? So far clear? So this is a new type of shape from X method that gives you intrinsic properties of the shape that even goes beyond where you can use light, right? Now, you might ask, well, this requires a video. What about moving objects? If I have to track something, what do I do, right? So let's think about how to track objects with this kind of an effect. And let me talk about one particular way of tracking this with thermal cameras. So what is the one thing that you need for tracking an object from frame to frame? You need to have texture. Every computer vision student knows how to do template matching. And if it's a blank wall, it's very hard, right? So now, of course, if you have a blank wall, you can project light and add texture to it. The problem is that if you move the camera, the texture moves with you, right? And so you can't really make the pattern stick on the object. And it's true even in the case of LiDAR, right? So if you have a LiDAR on a vehicle and it's going, it's illuminating different points in the scene at different frame rates, right? And so you will be able to estimate 3D at every instance in time, but you will not be able to track it, right? You don't look at the same point over time, right? And so how do we use a thermal camera to do this? Well, it's pretty simple. In fact, let's say you use a laser, some laser, LiDAR, it could be whatever, right? And you project whatever pattern you want, and you're moving your camera, right? And clearly you cannot track these points because every time you're capturing an image, it's a different set of points. There's no tracking possible, right? But because this is a laser, and if you hit a scene, it will generate a little bit of heat, a little bit, right? And it will conduct, and it will take some time before it completely diffuses out. It's not like light that it's gone immediately, right? So in fact, it stays there for a little bit of time. And so you can actually track those points over time, right? Because you have that a little bit of conduction that is going on, right? This happens everywhere. We use an ordinary laser. We use it for many applications. And you illuminate almost any object, you will see this, right? And so then you can run structure from motion, object tracking, optical flow, all of these things you can do, okay? Yeah, question?
If you were working for the military and wanted to develop a plane or an object that you didn't want detected from thermal imaging, how would you design it in such a way that you challenge your reconstruction problems?
There are materials whose emissivity is very low. Metals. Emissivity is very low. Conductivity is very high, really fast. And so you would need an extremely expensive thermal camera to get that signal in general, right? So if you had, but if you think about glass, other things, it's just not going to work, right? So you would have to have extremely polished metallic coating at least, right? That you will not see it at all. Yeah.
So what's the speed of heat in let's say glass versus metal?
So there are so many variables here in the heat transport equation, right? So there's something called the heat capacity. It depends on how much, just like a potential well in a camera, how many photons can you hold? So that changes with the thickness of the object. The heat capacity is thickness. So if it's an extremely thin sheet, it just doesn't retain any heat. It can get very fast heat very fast, and so on, right? So there's like 4 variables there. Some combination of this is going to tell you how much heat is retained, how fast the radiation happens.
Let's say on a typical wall or typical glass.
For example, if we had to track this, so let me just play this video and I'll show you, and you'll see the extent of this. By the way, I was talking about a blank wall, but you can do this wherever you have repeated texture as well. We know in computer vision, if you had repeated texture like windows and so on, tracking gets confused, right? And so here you can do it with repeated texture. So let me show you that video, and then we'll talk about it. So this is the tracking that you're seeing, right? So the lengths of the track, so you look at a couple of seconds. So it stays there.
This is the floor.
This is the floor, right? The length of the track is a few seconds, but that's good enough for Colmap. It's very useful, right? Just a few frames of tracking will allow you to use Colmap, right? And after that, you can turn, you can do all kinds of things, so you will see the whole thing being tracked, right? So this literally is getting rid of any complications due to surface reflectances. Right? You can do glass, you can do this blank wall, you can do repeated texture, except metals. And there are some materials, there's a whole database of materials that thermal imaging keeps, and there are some strange materials that have, that the conductivity is very, very high, right? And so you cannot use them on those, but almost all of the things that we see in this room, it retains heat for a few seconds. This is with an ordinary laser, right? And to just test the tracking, this is, I don't know if you guys have seen Smith Hall in building. It's a pretty long building, and we're going around, and we didn't do any loop closure or anything, but it's pretty close, right? So the tracking is pretty good, robust. Okay. Other questions? Yeah.
I guess one difference between like using light and heat is that heat also could deform the object itself, right? And you have to assume like
so this is the amount of heat that we are talking about is so small that it is not doing that, but you're right. I mean, there could be thermal expansion. In fact, there is something called photoacoustics. And so that thermal expansion creates sound and light and all kinds of other things. So there's, it's being exploited. But there could be a case where the material is, welding, right? You have huge power and you're going to melt the thing, right? So that part we are not considering here, right? We are assuming that the structure of the object is not changing, at least measurably.
So in the earlier cases where you're using like a heat gun on like a plastic bear or something?
Oh yeah, we have burned things, yes.
Okay.
Yes, we tried putting, because initially we didn't realize how much signal we needed. We thought we needed a lot of signal because these cameras were really bad. So we were using really hot air guns and burning paper cups and smoke alarms in my lab and so on. But it seems like we don't need that much. Once we figured out the algorithm, then we realized that we don't need that much of a signal, right? And so, yes, having a dark object helps because it absorbs more light, right? And that's what I want to talk about next. In fact, that's exactly what I want to talk about. So light transport, light does its thing. It reflects, refracts, interreflects, all kinds of things it can do. But almost always with any interaction, there's a little bit of absorption. There's no such thing as 100% reflectance, right? And so that adds up. So in fact, that becomes your heat generation, right? The amount of light received at the point is going to be the source term here, right? That generates the heat, right? And once it generates heat, you know all the three things that happen, right? But what I want to say is that whatever is lost in light transport is gained in heat transport, right? Some energy is absorbed here, it is seen here, right? Energy cannot be destroyed, it just can be converted from one form to the other, right? And so you can write an energy balance equation, energy conservation equation, that says, hey, you might have lost something here, but you get it. If you have reflectance of 30%, 70% is absorbed, right? So you can use that in this way. So for example, let's say you have an image like this, and these markings are really high reflectivity, right? Low amount of heat is going to be absorbed here than here, right? So if you think about any edge like this, right, you can say that, hey, in the visible spectrum, this is bright, this is dark, right? What do you expect in the thermal? It's flipped, it's opposite. Very simple, right? So you have at an edge, you have a constraint that says the polarity of this edge reverses. That means it's likely a reflectance edge, okay? But now let's look at this edge here, okay? So let me show that visible image edge. Now this edge is due to shadow, right? Because this is a ledge here and there's a shadow of that, right? Now in the shadow region is dark in the visible and it's cooler in the thermal. So there is no flipping of the edges, right? So that's what you see here. So you can think of a very simple classifier that look at these edges and say, hey, if there is a flip in polarity, it's a reflectance edge. If it's not, then it's a shadow edge, right? And so this is a classical computer vision problem. Edge detection and classification is something that people do with deep networks now and so on, right? Here's a very simple way of doing this, right? So you can classify these as reflectance, these as shading edges, right? But what we have also shown is that you can actually do a comparison, not just across edges, but you can take any 2 points here, and you can see which brightness is higher in thermal versus visible, okay? And that ordinal relationship, it says this is brighter or this is brighter, tells you something about how much light is being absorbed in the 2 points, which one is higher, and how much light is being received at the 2 points, which one is higher, right? And so this is an ambiguous problem in computer vision, right? So you're capturing an image, which is a product of however much light was received at a point, and then a fraction of it gets reflected, right? It's a product. When you have a product, you can't just separate that easily, and that's called intrinsic image decomposition, right? And because we have a way to do it for any 2 points, we can give a signal to let's say a neural network that says, hey, the reflectance is higher here, lower here. The shading is higher here, lower here. So you get lots of these supervision. And then you can throw it into a network to say, what is the reflectance and shading at every pixel? Okay. These constraints are so strong that this neural network just converges very fast. Okay. And so here's what it looks like. So this is an image. It's a strange image. You guys know what this is?
Like a dinosaur?
It's a dinosaur, actually. It's a dinosaur. We have a dinosaur museum right across our street, and kids come there, so there's all kinds of letters and text and so on, right? And so this is a thermal image of that thing, right? Bright sunlight. And if you do this type of supervision signal, you can actually separate the albedo, which is the texture, pure texture, versus the irradiance, which is the shading, the amount of light that reaches each point, right? So the sun is coming from this side, so the light is much greater here. You can see that here, right? And so you found a way to take a product and you separate it out, right? And so this is called intrinsic image decomposition. And we tried a bunch of deep networks to try this. It just produces garbage.
And what happens at your occluding edges?
Sorry?
Your occluding edges?
Very good question. So depending on the relative intensities in the 2 different cases, it will either say it's a reflectance edge or it could go one way or the other. Yes. In most cases, this occluding edge just comes out fine in the deep network. The deep network does at the occluding edge, it knows what to do, because we have given these pairs everywhere, and we're using a prior of the deep network. Yes. So here's another example of this is a much simpler scene. You have a set of stairs here. What's interesting is that you see the shadow here, you see the bars here, the actual bars, And if I show you the decomposition, look at this. So there is no shadow here, right? Because you know that is the case. But what's interesting is, and the shadow is of course here, but what's interesting is if you look at these bars, they're dark, but they're also receiving a lot of light, right? In fact, they're receiving almost the same amount of light as the wall behind, right? And that's what we show here. It's almost the bar is gone here. That means it is actually receiving, it's facing the sun, it's almost receiving the same amount of light as something behind, right? And so this kind of decomposition is very tough to do, right? Because of, and we've used about 7 different deep networks and they all do really weird things, okay? So this notion of energy conservation that says whatever is lost here is gained here, right? You can do that in a scientific experiment, like, think about photosynthesis of plants, right? So this is called leaf energy transduction. Energy transduction just means converting one form to another, right? And if you look at a tiny patch here, this patch on the leaf receives light from the sun. Some of it goes out, reflects, some of it goes through it, and so on. Whatever else that didn't escape out is available for the leaf to use, right? So that's called the net absorbed light. Now, what does that do? Now, if you have chlorophyll, those molecules, they just rise up in state, right? They go to an excited state. And when they come down, they release energy, and that is the energy that they use to do photosynthesis. And in fact, that energy typically is too much. It's like food. Today we went to this Lebanese garden and they gave us a huge, I can't eat all of it. The rest of it I throw, right? Plant also does that, right? In fact, it throws out energy via fluorescence, right? So whatever wavelength you get, it shifts that wavelength and sends light out in this 650 nanometer range, strangely, right? That is one mechanism it does. Too much food throws it, right? It uses just the amount of food that it needs, depending on how efficient this plant is. It uses some metabolism, right? Some energy for metabolism. What do you think happens to the rest of the energy that is absorbed? Heat, right? So the same thing, right? So now you can write this sort of energy conservation equation that looks at, hey, how much metabolism does the plant using? And it's the net absorbed light minus the amount of heat that it's dissipated minus the fluorescence, right? So it's just energy conservation. Now, of course, this equation, the problem is that this variable is very complicated because it depends on how much light fell, what is the angle of the leaf, how much light got reflected and transmitted. This is a very tough term to estimate in the field. It's almost impossible to estimate that. But there is one amazing property of light transport, which is it's linear. So if I change the amount of light, if I make it double, let's say I'm using grow lights and I use double the intensity, what would happen? Well, this part remains linear. This part is like twice, right? And so when you do a second equation where it's twice, you can just cancel that out. It's a linear system. But what's interesting is what the metabolism is, it's not linear. Right? It's like saying somebody put food on your table, and depending on the amount of food, you're going to finish it. That's not possible, right? Depending on how much hunger you have, what kind of capacity you have to do metabolism, that is the amount of things that you eat, right? And so the other terms are not linear. So this part goes away, right? And so the rest is obtained by just taking a difference of changes in light levels. If you know how much change in light level there was, maybe a light meter or something, right? That is sufficient to see what is the change in metabolism that happens as the light level changes. The sun is there, cloud moves by, right? This is how the plant adapts, right? And that can be measured using these two things. This is called the excess heat, and this is excess fluorescence, okay? And in plant literature, for some reason, they did not write this equation. They were only measuring this. And they were saying, this is equal to this, right? And this works if you do something instantaneously. They would put a leaf clip in the lab, they would spike a huge pulse, and it would go away very soon. There's no heat generated, and they would ignore that. That cannot be done outdoors. This is one of the reasons you cannot measure photosynthesis easily outdoors, right? But now you can, because you have that heat energy that we can observe, right? Because we know how to solve the heat transport equation, and it gives you the amount of heat that generated all of that heat dissipation from that equation. That's what you need to subtract, right? And now you can now see these kinds of images for the first time. So you have some basil plant. You can do all kinds of things. You can say, you can starve the plant for a while. You can add water later. You can see what happens. What is the plant doing, right? So this kind of sort of a whole image of things is what happens at every location. So for example, in this particular case, there is a lot of change in photosynthesis that happened, right? And maybe after a while, it had enough of eating, and you don't have that anymore, right? So this kind of thing is a completely new signal for plant biologists, right? So you have this whole signal where they were always looking for one point in the lab with just some very $50,000 equipment thing, where they control the gases and everything. Here you can just keep a camera outside and look at what the plant is doing, right? And so we are working with a bunch of agriculturists in different universities to add this thermal camera to their setup, right? Okay, questions on this? Yeah.
So you measure the fluorescence as well?
Yes, so you can do fluorescence and heat. What we have seen is that heat has a much, much bigger component than the fluorescence. So if you didn't have the two devices, you're better off measuring the heat.
Right, if you have to choose one.
Yes.
So for the fluorescence, you need like a very specific wavelength.
Correct. So there are devices that measure exactly that wavelength, right? So there is a sensor that is developed. In fact, they do something called solar-induced fluorescence on the satellite as well.
Okay, but for the heat, it sounds like you're not mentioning that this should be at a specific wavelength. This could be anything in the thermal, or should this be, are there any wavelengths that are better?
This is from 8 to 14 micron. It's a wide band.
Okay.
But the entire heat energy, right? So there's no band here, right? The fluorescence is very, very narrow band, 650 something. People have seen that because that's what the chlorophyll molecule does, right? And there are amazing equipment. It's put on satellites now, and they measure that, right? The question is whether both these components act or not, and it does act in many cases. So we need to measure heat. Yeah.
So from the visible to 8 microns, there isn't much happening?
So no, why do you say it's?
Oh no, I'm just asking. Like
No, it does. But it's so that's a very interesting question. There's a project that I don't have it here, but let's say that you take an image with a visible camera, visible spectrum RGB, and then a thermal, right? The thermal is not just about absorption in the visible spectrum; it's absorption throughout the entire spectrum, right? So let's say sunlight, right? Sunlight has wavelengths throughout the spectrum. The visible spectrum is only a little bit. So the missing energy, for example, swirl and midwave and all that, that information is already also in the thermal. So in fact, what you can do is use the same energy balance to compute what a SWIR image looks like using visible and thermal. And so that kind of energy balance works there as well. So the thermal energy is generated because of all wavelengths, not just visible. Right? So it's a pretty interesting problem that maybe a midwave IR camera is very, very expensive today. But if you have a thermal and up to short wave, you can find the missing energy. Right? Yeah.
I guess here you're measuring like the radiation given off because of heat, right? But to do the heat like energy conservation, to measure the heat that's actually in the material there, it requires like a lot of knowledge about what the material properties are.
Oh, so that's the heat transport equation that I showed maybe 15 minutes ago, the long equation with lots of, if you watch a video, we show how to estimate all of these things.
I see. So like
Yeah.
if you have a plant where the material is not homogeneous, there's a lot of complex
That's
structures,
fine.
I guess.
That's fine, because what you want is time. So a single pixel through time is what we're using. Of course, some of these parameters, for example, heat capacity and so on, they are very uniform across the leaf. So while the method does not require it to be homogeneous, if it is homogeneous, you get a better solution. Yeah, that's a good question. But that's the basis of all of this, right? So in the beginning of the talk, I showed that long equation. We know how to estimate all of those things from video. That's the take-home point. Yeah.
You said that there are these expensive equipment for measuring fluorescence images for these kind of applications. But
Yeah.
how did you do it then?
Oh, thermal camera.
Just thermal. So you just measured the heat part?
Yeah. So the fluorescence part, somebody has already done it.
Okay.
Right? Some part of it is already. What they use it in a situation where the heat is not generated. So they capture extremely short time intervals. That's not, I mean, it's like the instantaneous response of a plant. Is that the only response of a plant that we need to look at? Because, there's no such thing as instantaneous response in a plant, right? You're human beings, the same thing. It takes some time to open the stomata. It takes some time to collect, sunlight. It takes some time to do a lot of these things. So these instantaneous measurements are not an indicator of what happens in the field, really. This is really good for biology and understanding molecules and how they work and so on. But you really need to measure these things in the field at longer time scales, at least seconds. And for that, you cannot use fluorescence. You have to use heat, or you have to use both. Yeah.
Did these biologists drop the excess heat because they did not believe that heat was being generated?
No, because for some reason, they did not know how to generate the source term. They did not do that. Because just the observation is not going to give you anything. You have to fit it to the heat transport equation and generate the source term. That is what this is.
But
that part was missing.
But they're aware that heat is being generated.
Of course, yeah. So they've shown videos of heat, but that's not the term that you need for this. Yeah. Okay, so let me, I don't know how much time do I have? 15?
Well, 15 minutes.
15 minutes, okay. So, but that's fine, if you have more questions, we can always stop you guys. So let me, switch gears and talk about sound, because I said heat, light, and sound. There's again several projects where we combine heat, light and sound. One of the first ones that we did was a few years ago was called dual shutter vibration sensing, right? And if you think about seeing the sound, right? So sound creates, vibrations. I'm talking, there's vibration of my vocal cord. I'm talking, and even though you can't see it, this screen is vibrating because I'm talking. And I'm walking, so all of this thing is vibrating, right? We just cannot see it with our naked eye, right? So you need something that is special, right? And more importantly, a camera is a spatial device. That means I can see you all parallelly in the same image. A microphone is not like a spatial device. So if you put a microphone here, if all three of you talk, you get the sum of that, right? And so that's the big difference between camera and a microphone, right? So you have here guys with two guitars. Let's say they don't like each other and they start playing their own songs or whatever. And a camera can, see the two guitarists very easily. It's obvious, right? It's so obvious, right? But a microphone captures the sound of those signals, right? And in addition, maybe there is echoes, right? Which you don't want, and you definitely don't want construction stuff going on. It's all being captured by a microphone, right? Camera can see all of these things differently, right? So if we actually are able to see the vibrations independently at different locations, we can actually capture the audio independently and simultaneously at different locations, right? So maybe you look at the body of the guitar, and if you see very, 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 very tiny shifts, right? And if you do that at 2 points on the two different guitars, you get audio. right? And so this is exactly what we did a few years ago, and this is called dual shutter vibration sensing. That's the first one, right? That is the audio that is seen by our camera, right? And this one is a little bit low, but you can hear it. This one is the audio at this guitar, right? So now, naturally speaking, we are able to see these vibrations. You have a question?
Under what conditions can you assume they're independent like that?
Oh,
The second guitar isn't going to bleed its vibrations into the first guitar, right?
Oh, yeah, but that, you mean like this guy is walking and maybe there is this and there's something else. That part is much smaller than the sound. So you're right that there is sort of sound also is behaving like light and bouncing
That's
around
right.
and so on.
Right.
And I'll show one example later on what it does. But here we're saying, hey, there is a dominant signal here, there's a dominant signal here, I can get audio. And of course, this is not easy to do because partly because of engineering, right? So you have to measure something with very low amplitude with very high frequency, right? And that's hard to do with a regular camera. And so you either may have a very big lens or maybe a very high-speed camera. If you use a high-speed camera, you need a strong light source to illuminate it, and so on, right? So, and this has been done. This has been done, right? So, as a proof of concept, you can actually do this, right? So, you can actually take a high-power zoom lens, look at a small point, and you can actually measure the vibration, right? But that means it's not that practical, right? And so in this particular case, what we are doing is something that is well known in optics. This is called the memory effect. And so if you use a coherent light source like a laser, right? Of course, if I focus on this laser, it just looks like a dot. Nothing happens, right? But if I focus somewhere other than that location, you get interference of light waves because it's a coherent source. There's light waves that are reflected, and you get interference, and this is called speckle, right? And this memory effect says that when you have really tiny changes, right? Changes in this orientation, this speckle basically shifts, right? This speckle basically shifts. And this is a way to actually magnify optically the tiny vibrations that you're seeing, right? And once you see a speckle shifting like this, correlating this is very easy, right? It's just one line of code to correlate this, right? And so you can deal with the amplitude. The second thing is you also need to deal with the speed. And in this particular case, we are using a sensor, which is a rolling shutter sensor, right? Everybody knows how a rolling shutter works. You know, so in one row by row, it is reading it, right? It's a high-speed camera in all of our pockets, right? So if you have 1,000 rows in your image, and you want a 60 frames per second camera, this row is changing at 60 kilohertz, right? So you have a high-speed camera, and you're watching for a 1D signal, basically, right? And so that's what you can do by a combination of a global shutter and a rolling shutter. You're able to get both low amplitude and high frequency in this case, okay? And so, again, I'm not going to go into the detail of all of this, but here's what it does. The cameras do when you're looking at the membrane of a speaker, right? The speaker is playing something, and this is really, the correlation between the speckle here and here. You shift, you find the shift, and you get the audio signal, right? And the audio signal. It's like that, because I can't use more than a few seconds. So copyright, but one of the things that is interesting is this indirect sound. Okay, there's this beautiful paper. I don't know if you guys know this in 2014 by Bill Freeman's group. I was so impressed by this. And it's called Visual Microphone. They really built with a high-speed camera and everything, and it showed proof of concept, right? And what they did was, one experiment was they had a speaker and they had a chips bag, and the speaker was blaring something, and the chips bag was vibrating because of that, right? And this high-speed camera with a strong light source and a very strong speaker was looking at that, right? And so this is what they actually heard. This is what they heard with $100,000 equipment. big speaker, they were fluttering this poor chips bag, right? And now we can do that with just an ordinary speaker, with a chips bag, with an ordinary camera. So it's very scary, right? And I'll play this music.
Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, that lamb was sure to go.
Quality was significantly better, right? And so with huge amount of equipment and cost and all that, they showed this. It's amazing, this indirect sound, right? So we are able to capture it at much higher volume with much less signal and so on, right? So that was interesting. Now, this doesn't have to be an audio signal. This actually, it can be a wave in any surface, right? So imagine you think about a wave, ripples on water, right? So if you drop a stone, you see the wave, right? This vibration camera can actually see this wave, right? A very, very tiny wave. So if I knock here, this is vibrating and I can see it, right? And so the interesting thing is that now, if you can see how the wave is expanding, so the direction of propagation of the wave, if you know that, then you can sort of say, where was the stone dropped? You backtrack it and you say, where was the stone dropped, right? And that, you know, even if you don't see the location of the stone where it was dropped, maybe there was a tree there, right? It doesn't matter, right? So you're only looking at the wave propagation direction and then you're extrapolating it, right? And so here's an example of what we did. It's a sort of toy example. Yes, it's Canada, so I should say table tennis, not ping pong. In the US, they don't know what table tennis is, so ping pong. So you have a table tennis table here, and you're hitting the balls, and the balls are hitting this table. Now, we placed a camera under the table, okay? It's observing the vibrations from underneath. It's not seeing where the ball is being hit. It's just seeing the vibration, right? And we can, you know, predict where the ball was being hit, right? So you're actually observing the vibrations everywhere. And sometimes it's not just the location, you can measure the force, you can measure if you hit a smash, it's not, you know, it's sort of skidding, you can see that effect as well. So all of that you can do. Yeah.
Do you get information about the shape of the surface too? Or like, these are flat, but what if the object wasn't flat?
Correct. If the object had a shape, then you have to solve that shape problem. We haven't done that. We are assuming locally flat shapes. Absolutely, yeah. Okay. Okay, yeah, go ahead.
Yeah, I mean like the what's the FOV of this camera?
What is the
FOV, field of view, or like is there any like the depth?
No, I mean it's a 30-40 degree ordinary field of view, right?
Mm-hmm.
There's no, you're not looking at one point. You're looking at a full field of view, right? And you're measuring, depending on where you can send the laser point, right? It could be any number of, you could throw a, you know, laser light show, and there are lots of points. You can measure the audio at all of those points, right?
Okay.
Yeah, so the field of view is pretty much the same as a normal camera.
Oh.
Yeah. Okay, the last part I want to say is, so far we measured sound at the audible range, right? 20 kilohertz, 30 kilohertz. You can go up to 60 kilohertz, which is beyond our audible range. Well, what about megahertz? Right, ultrasound is megahertz. Right, so what do we do with that? Now, I'm not going to say we're going to observe the megahertz, but we're going to use the megahertz to do something with light. Okay, and so one of the examples that I'm going to talk about is how to focus light deep inside tissue. So if you have a, you know, everybody has a cell phone. So if you run your, what is that? This thing, you can see that the light passes through your finger, right? We are a very translucent body, but the detail is lost. I mean, there may be a tumor there for all I know, right? But the detail is lost, right? So how do you focus light deep inside? This is a very, very challenging imaging problem, right? Why? Because, you know, when you send light here, it just gets scattered everywhere. It's an extremely inefficient system to try and push more light into this tumor. It's like banging your head against the wall. Right, you will not get it, no matter how much power you have, right? And so this is a problem. Now, of course, if there was no tissue, if you had a lens, everybody knows how to focus, right? So everybody, this is straightforward, right? But when you have a tissue, this light rays don't go in the place where you want them, and they just go everywhere else, right? And so somehow, the problem is once the light leaves the lens, I have no control over the light. I don't know what to do, right? But what we can do is, if we can somehow control the tissue, right? For example, by changing somehow the refractive indices, so that you can try to bend the light back, right? And so how do I do that? Well, you can do that by using ultrasound. So ultrasound is just, everybody knows ultrasound, right? And so it creates the pressure wave at megahertz, right? Tiny, of course, it's not so hard that your tissue gets damaged. We know exactly healthcare-wise how much voltage and frequency you can use and so on. And so you have this pressure wave, right? And so this changes the amount of density, right? As the wave is progressing, it changes the density. When it changes the density, it changes the refractive index, right? So if you're able to control that, then you can try and do some amazing things, that you can take this light beam that is coming in, and you can use the tissue itself as a lens, right? So it's a gradient index refraction lens that continuously changes, right? Refractive index, and then you can focus, right? Now, of course, here I showed just water. There's no scattering. And what we have shown is that even when there is scattering, there is recycling of photons that were originally lost. They get back. Not all of them do, but a significant fraction do come back, right? Because you're sort of forcing it to come back. It wants to go like this, but you're forcing it, right? So the amount of the game here is how much photons can you send here, how deep, and what is the resolution. That is the game, right? That is what we want to do. And so here's an initial setup. Again, it's a lab setup, right? So the ultrasound is going through some liquid or some other medium, and if you turn it on, it just focuses really nicely, and then there's the CMU. Now the challenge, of course, is this is a very hard imaging problem in this that we have to optimize the ultrasound to make light do what we want. That's not easy. You can't just think that you're going to be able to do this. And we really realized that you need to have a good simulator to know what the ultrasound parameters, how they are controlling the light. There was no easy way for us to understand that. And so we built actually a simulator, and I'm going to go through that very quickly. Don't worry about it. It's just what happens when you have a refractive medium, right? So light doesn't go straight, right? Like in a mirage, light curves like this. But when you add scattering, you get light going some weird ways. Instead of just saying straight, 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 you go to curve like this, another curve like this. And so simulating this is not straightforward. And ray tracing this is very tough. And a few years ago, we wrote a SIGGRAPH paper that combines these two things. And this is a, I don't know if this is, you need to switch up there, it's better. You can see how we can create, this is a glass ball with different refractive index profiles. It's called a Lüneburg lens. And you can shine light and you can create different kinds of interesting refraction. And if you're wondering what's here, this is just fog. So there's scattering as well as refraction changes, right? And so if we do this, so we figured out what is the optimal parameter to increase our light throughput at this location. That was very important from the point of view of the simulator, right? And so now we can generate different kinds of parameters to create like hologram kind of thing within a tissue. You can focus at different locations. If you know that there is a tumor here, you focus there. If you don't want to focus, you want to focus behind a tumor, you can do that, right? Literally like a hologram, right? And so you can do this sort of designer-based focusing of light. So here's an example of an actual tissue sample. And so you can see the big difference in the kind of point spread function that we get because you're sending more light through it. And this is a very, very tough problem because each millimeter is an exponentially harder problem than before, right? So it's not that easy to say, hey, I sent light through 3 millimeters. This is very, very tough, right? And so this kind of thing, hopefully, what we have seen is that there is enough contrast here that we can go about 4 millimeters in brain. Okay, and that is the full depth of the cortical structure of the brain. Right, so we can actually look at the bottom part of the cortex with this, right? And so with some colleagues, we are actually looking at that. One thing I didn't say was this thing can also be scanned really fast because its ultrasound can just be changed and you can do it up to about 1,000 times faster than a LiDAR without any moving parts, right? Because you're controlling these waves at megahertz speed, so very, very fast, right? So in fact, one of the things that we are now working on is on a rodent brain to try and image this thing, right? So there's a bunch of people in UPIT, brain surgeons and so on. Because now we have the theory to say, yes, we can actually go the full depth because we've shown it on samples, right? So the question is, can we measure live the brain, the functional imaging of the brain at cellular scale, right? That's what we want to do, okay? Unfortunately, I don't have anything to show on that, but this is the future work that we are going towards. Okay, so with this, I just wanted to say that we've been chasing the dream about getting to human vision in computer vision, and we are very, very close. You give an image to a VLM, it says what's in it with great accuracy. The question is, how much further can we go beyond human vision? And hopefully I convinced you with all of these projects, you can expand the boundaries of computer vision. Thank you so much.
Wonderful, wonderful.
Other questions?
Questions?
Yeah.
Why would you not, so for the last project, why would you just not use an ultrasonic phase array for ultrasound imaging, and what are the specific?
Oh, resolution. So the resolution of ultrasound sensing is so poor compared to, let's say, OCT. So we would use optical coherence tomography for this, because what we want to do is every neuron, how it fires, we need to see, right? And so that is, in brain science, they're thinking about that as a deep question. With ultrasound, you don't have that capacity. In fact, with MRI, you cannot do that, right? MRI is much higher resolution, but you still cannot do that, right? Optically is the only way to get that kind of resolution, unfortunately. But the optics means, with light means you have scattering.
But this is defined by the size of the ultrasonic transducers, right?
Well, in theory, the engineering of this thing, how many transducers you need to generate that kind of resolution is just infeasible. There are, I don't know if you know Li Hong Wang and others who are doing photoacoustics. They have a very expensive array, right? But you cannot go below maybe 400 microns or something, right? And we are looking at 10 microns or 5 microns. So you just cannot do that. It's that I know of. Just the wavelength is different, right? So there is a fundamental limit that says you can only reconstruct up to the wavelength of whatever your signal is, right? And that is not there. Yeah. Other questions?
So in that case, you only talked about focusing the illumination, right?
Yes.
And then what about the capturing side? Is it going to be fluorescence?
So there are many ways of thinking about it. So one you can do, one of the projects that we are working on is to send light using our method, but receive information using photoacoustics. Okay. And so if we are able to, so the way photoacoustics works is that you're sending a laser beam, you're heating that spot up, then it expands and it creates photoacoustics, right? An ultrasound wave. And the problem is, for the depth that we need, it's almost guaranteed that you're going to burn through the tissue. Because the amount of light that you need at the deeper location, you would use a higher power beam, then it's just going to burn the tissue through, right? So there is if you can deliver at least better, it's like round trip. There is a round trip. One of them we can solve. The other one could be 2-photon. There could be other kinds of OCT or even diffuse optical tomography and things like that. Yeah. Yeah.
So in the equation that you showed for the plants, where you had the metabolism and the fluorescence and all of that, that equation didn't seem to have a time in it. But as you mentioned,
it's of T.
Right, but what are the time constants involved, right? Because some of them are slower, others are faster.
Absolutely, absolutely. In fact, the lightest time constant is very narrow, right? But there is enough light that if photosynthesis doesn't happen instantaneously.
Right.
It depends on whether the stomata is open fully or not, and it takes a while to open, and there's a whole range of things. The plant is much, much slower than light, right? And so we always take energy that goes for maybe 10 seconds to capture this video, right? So the fluorescent based guys, they do it in instantaneous, almost instantaneous. So they say there's no heat generated in a extremely short pulse, and they can sort of ignore the heat and everything, and they do it at the speed of light. But it doesn't mean that I can just convolve that, because it is non-uniform, right? So you need a different mechanism for a different time scale. And so you need to be able to collect enough photons to do that time scale. So yeah, I don't know how to maybe do some deconvolution to do something, but it is, the more we read, the more complex. It's like the human body. How we eat food, and there's so many things that most times we read it and there's light reactions, dark reactions, this chemical reaction. Sometimes the plant has to grow, there is a fruit bearing capacity. Well, some of that energy goes there, right? It's very complex. So all we can say is, look guys, there is some change in metabolism that is happening. I don't know what it is due to. The biologist should look at it. But we will at least give you like a loss function for a plant, right? We just say this is the change in metabolism that is currently happening in over a few seconds period. Whether it's going to be useful, I don't know, honestly, because we are still working with people because they haven't seen this. It's very hard for them to accept it because they're used to doing it with their $50,000 device in the lab with extremely short pulses. Time will tell.
When you said that photosynthesis was instantaneous, do you mean like the whole process?
No. I didn't want to say that. But yes, the light, chlorophyll molecule excitation happens, then the energy is released. The problem is the way it does is that it stores it in some protons first. So the energy doesn't just get immediately used up, right? Like you see the reaction, right? The chemical reaction. It says light on the arrow. It doesn't work like that. So it takes that energy that the chlorophyll molecule, while coming down to its normal state, releases, then that gets stored in a bank. Think of other protons that store energy. And so it's like saying you got lunch to go. You're not eating it right there. You buy it, right? And then you take it home and you eat it sometime. So plants can do that too.
I feel like a year or two ago, they were studying how long, when does photosynthesis start? But that's a different question, I guess.
Yeah, so that's why I'm saying I honestly don't know all the mechanisms that happen. I know that increasing light just suddenly doesn't make it use it up, right? And that's why it's not linear at all. That's the nice thing about it. If it was linear, we were screwed. There's no way we could solve the problem. It is non-linear, and therefore we have a shot at it, right? And there are something called dark reactions, light reactions. These protons are saving up, and after a while, there's too many protons, so it does something called light quenching. It just throws out. It's unhappy. More light comes in, it's very unhappy. It just throws out everything, right? It's a living being, right? So I can't say that I understand all of this, but I know that heat is just an important component here. how can we use that heat to go back and understand what's happening? I don't think that we have the time scale for that or understanding for that. It's too complex a process. But hopefully, in a machine learning algorithm, they use 20 features, right? This could be one of the features. That's what I'm thinking, if it at all is useful. Yeah.
For your last part, the future works with you're trying to probe skin or tissue with light, and the ultrasonic emitters will look like a rat's cranium.
We haven't done that experiment yet, but I'm just telling you that we want to do it.
Right.
So we do it with tissue samples.
You mentioned that you try to manipulate the density to bend the light inside in the flesh. How does that work?
Oh, ultrasound, right? Ultrasound. So you have a transducer, right? Vibrates, but it vibrates at megahertz speeds, right? So that transfers the energy. So that's why your ultrasound device is touching your, how they see if you have a baby or something, right? And so they do ultrasound. So it's touching it. There's vibrations, and that vibration go, and then they reflect back, right? There's a sensor. So in that particular case, sending energy and receiving energy is all in ultrasound, sound, right? Here we're talking about using the ultrasound, and those waves have been sent, and there's compression and rarefactions. Like a sound wave goes through air, right? From me to you. There's longitudinal waves like this in the air. So that changes the densities, right? And if you send light through those, the density is changing, right? Now, of course, in air, the density change is extremely minimal. In solids, you can create a big density change. And so that is what is allowing us to curve the light to come like that, right? So it's a pressure wave, just creates density changes.
So would you want to manipulate the phase of the ultrasound signals in order to
Yeah. So
that specific
there were some slides that I didn't show, but I think the controlling the ultrasound is not straightforward.
Yeah.
That's why we had to build a simulator. We had to build a very accurate renderer to then say what is the voltage and frequency that we apply to this transducer. And then it seems like the simulator is pretty good now. And we are able to optimize the exact parameters so that you can send light there.
And this is published in SIGGRAPH?
Well, the simulator is in SIGGRAPH. This other thing is in Nature Communications, yeah.
Okay, let's thank Srinivas one last time.